Okay, so we will continue with the dynamic programming strategy, applying on various problems to solve. In the last session, we have already seen how dynamic programming can be applied on the knapsack problem, as well as we have seen how dynamic program is applied to compute all pairs shortest path. That is Floyd-Warshall's algorithm. Now we will continue with the dynamic programming. This is the other topic, that is optimal binary search trees. Now, the problem here is that we are given a tree, a binary tree. Remember, we are talking about binary tree and binary search trees. Now, obviously the property of a binary tree is that you have at most two children. A node will have at most two children, and except the leaf nodes. And search tree is the left node, the data in the left node or the element or the left node will be smaller than the root, its root or its parent, and the right node will be, the right child will be greater than its parent. Now usually we have seen the binary search trees in terms of numbers, that is 10, 20, 30 or any integers. But binary search trees can be applied to any type of data. The thing is, the elements, whatever we are trying to create or build the binary search tree, should be comparable. For example, in this case, we have a set of elements, that is 5 elements. We have do, for, if, int, and while. Though you can take numbers also, it can be applied on numbers also. This problem can be applied on numbers also. But here in this case, if you see do occurs in the dictionary before for, if occurs after for. So that is how we can compare these elements and create a binary search tree. So the order of the elements is nothing but the dictionary order. To determine which one is greater than or which one is less than its parent. Now here, if you see, for a given set of numbers, there can be any number of binary search trees. You can find a binary search tree on the left side, which has for as the root, do as its left child, and 3 elements, 3 nodes as its right child, right subtree. Then on the right side, there is another tree with the same 5 elements or nodes, but the structure of the tree is different. It all depends upon actually the height. So both these are trees, binary trees. Now the thing is, let us look at how many comparisons are needed to search an element. Now remember, right now we are talking about successful comparisons. So if you consider this tree that is on the left side, for is the root. So if we have to find for, we need only one comparison. We compare with the root, it is found. What about do? To search do, what we need to do is we have to start from the root, compare the root, so that is one comparison. Then for the element do, what we are trying, which we are trying to search, is on the left side, or it's smaller than for. So we search the left subtree, and at the root of the left subtree we found do. So what we did is we needed one comparison to compare the root, then the second comparison to compare the left child. So there are 2 comparisons. So the numbers on above the nodes or beside the nodes, what you see, are nothing but the number of comparisons that are needed for successful search of each element in this binary search. So we need 2 comparisons. While also we need 2 comparisons, that is to compare for and then compare while in the second node, the right child. Then for int we need 3 comparisons because we have to compare for, while, then int, and we found int, so we need 3 comparisons. Then for if we need 4 comparisons because we need to compare the root node for, then its right child while, then its left child int, and then its left child if. So there are 4 comparisons. So the total number of comparisons for this tree is 2 plus 1 is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We needed total 12 comparisons here for this tree. So on an average, to search an element of this set, we need 12 by 5 comparisons. Now let us look at the other structure of the binary search tree for the same elements, that is do, for, if, int, and while. Now this right side binary tree, if you see, we need one comparison for, we need one comparison or two comparisons for do. Same way for int we need two comparisons, and for if we need three comparisons, and while also we need three comparisons, because we need to search for, look at for, compare for, then compare int, right child or left child. So if is three comparisons, while is also three comparisons. So in this case, for this binary search tree, when the structure of this binary search is in this way, we needed total 11 comparisons, because 2 plus 1 is 3, 3, 6, 7, 8, 9, 10, 11 comparisons. And on an average, there are 5 elements, so we need 11 by 5 comparisons. So this way, which tree is better for searching? Obviously, the one which has less number of comparisons. So if we check the average comparisons in the left tree, it is 12 by 5, and the right tree, it is 11 by 5. So obviously the right binary search tree is much better than the left one. Now these are just as an example, we have taken only 2 trees for this 5 elements. So there can be several other structures that can be generated through this for these 5 elements. So in this case, the right tree is much better than the left tree. Now the problem of optimization, because we are talking about dynamic search, dynamic programming, and obviously we need to have some criteria to optimize the solution. To have some criteria so that we get the optimized solution. So now, before we move to the optimization part, let us discuss the earlier thing. What we have seen is only for successful searches. Remember, it's only for successful searches. For example, I can just try to search for an element ABC also, which we say is not found in either of the trees. So what will be the number of comparisons needed to search that ABC element? So here we have only seen about successful searches. Now let us look at unsuccessful searches, how we have to do it. Now what we do is we try to create an imaginary nodes for every, for a leaf nodes, as well as for a node which has only one child, or internal nodes which has only one child. Now the purpose of creating these imaginary nodes, and these imaginary nodes becomes the external nodes, is that to determine whether there is a successful search or it's an unsuccessful search. Now, for example, if you take an example of, if I'm trying to search AB, so obviously I have to compare with the root node. A comes before for, so it should be in the left subtree. Then I'll compare its root, that is do. Obviously A comes before D, so it's going to be on the left subtree of do. But when we reach the left subtree, that is all these brown nodes are nothing but the external nodes which we have created, or the new leaf nodes which we have created. So once it reaches this blank root node, that means the element is not found. So that is the reason we have created the external nodes. All the nodes which are in the box and the brown nodes, they are known as, they are the new external nodes, and determine, or they are the nodes where the search terminates, saying that it's an unsuccessful search. If it's a successful search, obviously it will terminate at any one of the internal nodes. So structure is same for both the trees. The only difference is that we have created some imaginary nodes known as external nodes, and these imaginary external nodes nodes are used for determining whether the search is unsuccessful or not. Now, if there are n number of nodes in the tree, in the binary search tree, remember, the external nodes will be n plus 1. So you yourself can count 5 are internal nodes, so there will be 6 external nodes. So always there is going to be one more than the internal nodes. Always the external nodes will be one more than the internal node. That's a normal property of a binary search tree. So suppose if we say that the probability of successful search is Pi, let us assume the probability of successful search is Pi, that is for searching for, do, while, int, and if. That we have seen how many comparisons are needed. So if the probability of searching is Pi, that is for successful search, and let us consider for unsuccessful search the probability is Qi. So what we have to do is, actually why we are taking these probabilities, because we don't know how many times for is going to be searched. We don't know how many times int is going to be searched. So actually we cannot say that if the height of the tree is less, then the number of comparisons needed are less. We can't say that way, because we don't know how many times the number is going to be searched. Obviously, if we say that there are equal number of probability, I mean all the elements have equal number of probability for search, successful search, then obviously the tree with the lesser height is going to be much better than the tree with the greater height, because of the number of comparisons that has to be made. But usually that's not the case. We have certain probability that is one element may be searched more than the other element. So that will have the higher probability of search. So that is what for successful search, let us assume that we have Pi. P is the probability for successful search and Q is the probability for unsuccessful search. Now Pi represents, I is the ith node. We number each node. So if there are n nodes, I will be from 1 to n for P, for successful search. Then what about unsuccessful search? Now remember, always unsuccessful search is one more than the successful search. Why? Because all external nodes, unsuccessful search end at the external node, so all external nodes are one more than the internal node. So that is why I value is going to be always one more than the, for unsuccessful search, I value is going to be always one more than the I value for P, for successful search. So that is what we have here. If Pi is for successful search probability, I will be from 1 to n, that is n is the number of nodes. And for unsuccessful search, I is one more than the I value for successful. So it starts from 0 to n. So we have added 0 actually. I mean, we will be considering 0 to n for unsuccessful search, that is the value of I, and 1 to n for successful search, that is the probability for successful search, P. Now, this gives us the, mathematically, we can come to an equation that the probability, obviously when the probability is considered, the probability should sum up to 1. So the probability of successful search plus the probability of unsuccessful search, that is the summation of the probability of successful search, that is all the probabilities of nodes, successful search, and all the probabilities of nodes of unsuccessful search should be equal to 1. Now with this equation we can come and derive a criteria to find or compute the cost of a tree. Now cost here is not in terms of, like in knapsack problem we had cost in terms of profit and all. Now here cost is not in terms of any profit such, no. But the cost is in terms of what is the probability of successful as well as unsuccessful search for a tree. So that will be the cost of the tree. So here if you consider, we have the summation of Pi plus summation of Qi should be equal to 1. So what we are trying to do is summation of Pi multiplied by the level. Level of whom? What? Of the node. A is the internal node. I range from 1 to n for successful search. So this summation of Pi into level of I is nothing but level is the root node will be at first level, then follows the its children will be at second level, its children will be at third level so and so. And for unsuccessful search, we have summation of 0 to n, one more. Then qi, that is probability for unsuccessful search, multiplied by level of unsuccessful search of an external node, level of the external node minus 1. So this formula will give us the cost of the tree. Now our criteria is to find the optimization criteria is nothing but to find the minimum cost of the tree. So whichever tree is going to have minimum cost, that is going to be optimal binary search tree. So minimum cost is our optimization criteria. Now let us move further. Let us look at a tree with 3 elements. Now we had just now seen the comparisons made for all, what do we say, and a tree with 5 elements. For calculation purpose, we are taking tree with 3 elements. Now with these 3 elements, we can create actually 5 different trees, and all are binary search trees. Remember, 5 different trees can be constructed, all are binary search trees. And the thing is, we have to find the tree with the minimum cost. Tree with the minimum cost. Each nodes or each element's probability is given. That is, the nodes are considered as A1, A2, A3, 3 nodes, and its probability is P1, P2, P3. That is 1 by 7, 1 by 7, 1 by 7. And probability for unsuccessful search is Q. So Q is actually we need 4, because for 3 node we need 4 external nodes. So probability of each external node is given as 1 by 7, 1 by 7, 1 by 7. As what we are saying here is that probability for all nodes for successful search as well as for all nodes of unsuccessful search is equal. Now we have to find the cost of all these trees. So we have 5 different trees that can be generated, or possibly we can generate 5 different trees using these 3 nodes. Now here, the numbers beside the nodes represents the number of comparisons that are needed. Now, if you see, remember the previous example, we computed how many comparisons are needed for each. Actually, the number of comparisons that are needed for each node, whether it may be an external or whether they may, it might be an internal node, the comparisons that are needed is nothing but the level on which that node is. For example, in this case, do, the first tree, do is at level 3, because while is the root node, it's level 1. If it's child, so it's level 2, then do is at level 3. So number of comparisons needed for do is 3. The same way over here, in the tree below that, while is the root node, which is at level 1, do is the child, will at level 2. So number of comparisons needed is 2. So whether it's internal node or external node, the number of comparisons that are needed is nothing but the level on which that node is in the binary search tree. Now applying the cost formula which we have seen earlier, that is the cost equal to summation of probability of successful search multiplied with its level plus summation of probability of unsuccessful search multiplied by the level of the node minus 1. So let us compute it for the first node, the first binary search tree. Here, when we use summation 1 to n, we have P1 multiplied by L A of A1 plus P2 multiplied by L A of 2 plus P3 multiplied by L A of 3 or A3. plus unsuccessful search is Q1 multiplied by level of E1. E is the external node. Minus 1 plus Q2, that is probability of second external node multiplied by level of second external node E2 minus 1 plus Q3 and so on. So for 4 external nodes, that we have 4 external nodes. Now the P1, all P1, P2, P3, Q1, Q2, Q4, all are, I mean, they all have the same probability. So that is nothing but 1 by 7. So A1 is at which level? A1, do. Do is at level 3 in this tree. So 1 by 7 multiplied by 3 plus P2 is 1 by 7 multiplied by level of A2. If is A2, it's at second level, so multiplied by 2 plus 1 by 7 multiplied by 1 because A3 is the level of A3, which is Y, is at 1. Plus we have 1 by 7 multiplied by external node. This the first external node, it's over here, 2. This is the external node. So 2 minus 1 plus 1 by 7 multiplied by second external node is 3 by minus 1 plus 1 by 7 multiplied by 4 minus 1, and the fourth external node is this one, which is 1 by 7 multiplied by 4 minus 1. Now this gives us the total as 15 by 7. So this is the cost of this binary search tree, that is 15 by 7. Now let us take the second binary search tree. Now in this second binary search tree we have the same formula. It is expanded here. The formula, we can find that the first external node is this one. So 3 minus 1 plus 1 by 7 multiplied by 3 minus 2, and all these nodes are same level. So we get the cost as 13 by 7. You yourself can do it and verify that it is 13 by 7. The thing is, you have to use this formula. Same way when we compute for this binary search tree, we get the result as 15 by 7. Remember, the external nodes are, under different orientation. So that is how we have to compute the levels and find which one is the, how we apply the probability. And finally, we get the actual cost as 15 by 7 for even this tree. Then for the next type of tree, this tree also we have 15 by 7, as well as for the fourth tree we have 15 by 7. Now among all these trees, which tree has the minimum cost? Obviously we can see that it is 13 by 7, and this tree has the minimum cost. Now remember, among all the trees, this tree has the least height when compared to all the other trees. But you cannot say that this tree is going to have, the tree which has the least height is going to be the minimum cost or the optimal binary search tree, because here we got the height, the tree with the least height as the optimal binary search tree, because the probabilities for successful as well as unsuccessful searches for every element are same, that is 1 by 7. But if the probabilities are different, we may get a different binary search tree, which may be an optimal one. Now this letters, same scenario we have, and we have but different probabilities. P1, P2, P3 is 0.15, 2.1 and 0.05 for successful search for 3 elements, do, F and Y. And probability for the unsuccessful search for external nodes Q1, Q2 till Q4 is 0.15, 0.1, 0.05, 0.05. And you can see here, it's the same 3 elements, and same number of trees, binary search trees, but the probabilities are different. So when we apply the same formula, you yourself can see, when we apply this same formula, I have calculated this one, and obviously I'm going to give these the slides for these calculations so that you yourself, it will be easy for you to follow. So what we have is we computed this and we have 2.65 as the cost of this tree. This using the same formula we have I've already computed here. There's several steps. Its cost is 1.9. Obviously, is less than the first tree. Then the third tree, it's 1.5. The fourth tree is 2.15, and the fifth tree is 1.6. So among these, same trees we have, I mean, same number of elements we have, same trees we have. But earlier we had same probability. So we had the second tree in the middle, which was the optimal one. But when we are saying that we have different probabilities for each element, then obviously it's the third tree, that is do, and if is the right child of this do, and while is the right child of if. So this tree has got the minimum cost, that is 1.5. So this tree is going to be the optimal binary search tree for these elements, that is 3 elements, and its respective probabilities. Now when the probabilities change, for example for same nodes, the probability changes, then obviously you may get a different structure of the optimal binary search tree. So this was all like a brute force approach of using the formula and computing all the taking different structures of the tree and trying to compute which one is optimal. Now this cannot, I mean, we cannot proceed this way because there are only 3 elements. We got 5 trees. If there are 5 elements, we will have more number of trees. So we cannot always try to take pen and paper and try to solve this. There should be some logic or some optimized algorithm to do this. Now that is where the dynamic programming comes into picture. So programmatically, we will now, we will see how dynamic programming strategy can be applied to solve this problem. Now, actually, the number of trees which we get for n number of nodes is nothing but a Catalan number, that is Cn plus 1 of n, and that is how it's defined, that those many number of trees will be created is, whatever for number of n, whatever Catalan number we have or we get. So anyway, the cost has to be calculated using that equation, and we have to proceed this. Proceed with trying to find the tree which has binary search tree which has minimum cost, and that is going to be the optimal binary search tree. Now, let us look at the dynamic programming approach for finding for computing the optimal binary search tree. Now, in dynamic programming approach, we will be computing the cost. We will be computing something known as the weight, and we will also be computing or storing the root at each stage. Root, who's going to be the parent of each node at each stage. Now, here, if you observe, we have 4 elements, A1 to A4. So we have 4 different nodes, and we have to create or construct an optimal binary search tree for these nodes, and we also have to find the cost. Now the probabilities are given because there are 4 nodes. We have for successful search, we have probability from P1 to P4. That is 3, 3, 1, 1. And okay, the probability for the unsuccessful search for external nodes, and it's going to be 1 more than the number of nodes, internal nodes. So we have 5 queues, and its probability is 2, 3, 1, 1, 1. Now, before we proceed, we will be computing the cost at each stage. I'll tell you what that stage is. Cost at each stage. And then we will save that cost in a matrix known as the C matrix. matrix C, where I actually in every matrix I represents the row, J represents the column. Now to compute that, what we have is we have a formula Ci comma j equal to minimum of C of I comma k minus 1 plus C of k comma j. This k will range from I to j, not including I. That is why we have I less than k, not less than equal to. I less than k, k less than equal to j, plus w, I comma j. This w is the weight, and this w weight will give us the probability. It's computed using the probability, and will give us that what will be the weight and how much weight has to be added to the total cost of the binary search tree, such that at the end, at the final round, final stage, we get the optimal binary search tree. Now weight will, the equation for the weight I comma j consists of weight of the, I comma j is the probability of jth node plus probability of jth node of successful search plus the probability of unsuccessful search for jth node plus weight of I comma j minus 1. That is from the previous step, what is the weight we get. Then this R, table R, is nothing but we store the root. That is nothing but which k gives us the minimum. That is for which k the I and j value of the cost will be minimum. That kth value will be the root. So here we actually have to compute the cost, but cost consists of a W, so we are also maintaining the a table for W, a matrix for W, and in our matrix we will be storing the root. Now the first stage is that we consider only one element or one node. We consider tree. Actually, we are now trying to construct a binary search tree which will be optimal. So at first stage, we consider each node as the root. Each node as the root. So the first stage, cost of 0 to making 0 itself, each node. Now each node means j minus I should be 0. That is, we will be constructing 5 different, 4 nodes are there, 4 different trees. Each time only one node will be its root. So I minus j is equal to 0 means I is equal to j. So here we consider do if, int, and y. Now obviously 0 comma 0 is for the external node, so it's going to be 0. Its weight will be 2. That is the probability of unsuccessful search. Then because there is nothing now, so all the values in the diagonal, if you see, of C will be 0. This is the initialization part. All the values of root, because there is no root right now, all will be 0. There is no root right now. Then the weight is with the probability. So the probability at the initially will not be any probability because nothing is there in the tree is blank, null tree. So P of j is not considered, but probability, because there is nothing, there is unsuccessful search. So Q of j is considered. So initially Q of j will be equal to, W of I comma j will be equal to Q of I. So here you can see the diagonal is filled. For 0 it's 2, for 1 it's 3, 2 it is 1, 3 it is 1, and 4 it is 1. So this is filled, the diagonal is filled with all the values of probabilities of Q. Now remember here one thing, probability always should be between 0 to 1. But here we are taking probability as 3 also, 2 also. So don't worry, the textbook, I mean the authors, or even here in this case also, what we did is we just multiplied that by some value to make it a whole number, so that our calculation becomes easy. So probability is not 3 actually. Let's say 3 by 7, 3 by 7, then 1 by 7, 1 by 7, and for unsuccessful search 2 by 7, 3 by 7, 1 by 7, 1 by 7, and 1 by 7. So assume that for to eliminate the denominator, we just multiplied it by 7. So just to make it as a whole number, we have multiplied by some value and assume that we did something and we are having now the whole number, so that our calculation becomes easier. But always the probability will be between 0 to 1. So anyway, let us continue with these whole numbers. So initially everything is, for W, it is the probability of unsuccessful search. For C, initially everything is 0. For R, everything is 0. Now in the next stage, we start considering only one node to be there in the tree. So when there is one node means we come to an formula as only one node, as j minus I equal to 1, because we have to fill these matrices. So when we are considering only one node to be there in the tree, and that node should be the root node, then obviously to fill this matrices, what we need is j minus I equal to 1, which will be j will be equal to I plus 1. So here, if I is 0, j will be 1. If I is 1, j will be 2. I is 2, j will be 3, and so and so. Now you will understand at the end of this stage why we have considered j minus I equal to 1. So j minus I, what is the weight? Weight of j minus I. So let's take the first element, do. Consider we have do as the only element in the tree, and that becomes the root. So we start computing W value. So W of 0, 1. Why? Because j minus I is 1. So j is I plus 1. So when I is 0, j will be 1. And k will be between I to j, not including I. So k will be I is 0, 0 less than k less than equal to 1. That means k will be only 1. So we are considering only one node at a time in the tree at this stage. So W of 0, 1, because W of I, j, 0, 1 is P of j, that is 1, plus Q of j, that is 1, plus W of 0, that is I is 0, I minus j minus 1. So j is also 1 in this case. So what we have is P of 1 is 3 over here. Q of 1 is also 3. So 3 plus 3 plus W of 0, 0. What is W of 0, 0? W of 0, 0, we have already computed. It's here in the table. It's 2. Plus 2 will give us 8. Now this is W value. Now same way we find the C value. So first we compute, actually for computing the cost, we have to compute cost C. But for computing the cost, what we need is we need the W value. So we computed W value first. Then we are computing C of 0, 1, where I told you the K will be 0, 0 less than K, and K less than equal to 1. So you can substitute this in the equation over here, what we have I for C of I, j, plus the W of 0, 1, what we are getting in from the equation of W, which is equal to minimum of 0 plus 0 plus 8, which is 8. So C value will fill it with 8. Then what is the root? root is nothing but the kth value. K we are getting as 1. So k, and that was the minimum. So k is 1. So here in root table we have stored 1 at the place of 0 to 1, or 0 comma I, 0 comma 1 cell. So in that cell we have placed 1, which is the root. Now what is this 1? 1 is actually A1, which is do. So we considered only one element, that is first element is do, and that becomes the root, and now the cost of the tree is 8. Then in the next step, we have to compute the second value, that is I was 0, I will become 1, j will become 2. So 1 less than k less than equal to 2 will give the value of k as 2. Only 2 can be there. Now what is this 2? This 2 is nothing but a of 2. So we are now making if as the root with no other children. Only if is there with the root. So the same equation we have computed. We computed the value of I from value of w from 1, that is w 1 to 2, which is 7, and c of 1 to 2 will be 7 itself, and root is 2 because k is 2, and that is if is made as the root node. Same way we fill up 2 comma 3. So 2 comma 3 is going to be 2 less than k less than equal to 3. So only value k can have is 3. That is the third element is made, A3 is made as the root. And we compute 2 comma 3 which we for w, which we get as 3, and 2 comma 3 for c, which we get as 3 itself, and 3 is the root for the string. That's the only element. The same way we compute 4, making while as the root. We compute the cost weight. We compute the weight for 3 comma 4, which gives us 3, and cost of 3 comma 4, which also gives us 3, and root of 3 comma 4, which is 4, because that's the only element, A4. So this is how we compute. Now why we have considered j minus I equal to 1, because in all three tables or all three matrices, we are not bothered about the lower half from the diagonal, the lower left from the diagonal. We fill up these matrices only for upper half, and we go till the last cell, which is 0 comma 4. That's the last cell. So we don't fill up the lower values. And why we are filling up all the upper cells? Because from the diagonal, because we will be considering no nodes in the tree for the first time. That's the diagonal from 0 to 0, 1 to 1, 2 to 2. Then we consider only one node. So that is why you got 4 values here. Then we take 2 nodes and compute which should be the root. So when we take 2 nodes, we have a combination here, and we fill up these 3 cells of the diagonal. Then we consider 3 nodes at a time. Among 3 nodes, which node can become? Then we consider 1 node. We consider 4 nodes. Among those 4 nodes, which one should be the root node? And once we find the 4th one, that is the 4th, the cell at this top right corner, that will give us the optimal binary search tree, because we will have 4 nodes. Among those 4 nodes, one will be the root node, and then we can trace it back and find the left child or right child. So this was for taking 1 node and constructing the tree. Now we will consider 2 nodes at a time and construct. So when we are considering 2 nodes at a time, and we have to fill these cells, so j minus I will be 2. So we will consider 2 nodes at a time we are considering. So obviously j will be I plus 2. So starting from 0, I as 0, we will have the limit as 0 less than k less than equal to 2. Now in this case, what all values k can have? K can have 0 is not included. K can have 1. K less than equal to 2. So K can have 2. So K will now be, we will be having two values for K, and for each of them we will compute. So we compute 0 to 2 for weight, probability of 2 plus probability of unsuccessful search for 2 plus W of I, which is 0, comma, J minus 1. J is 2, 2 minus 1. So we have, you can look at fill up these equations, compute these equations and fill up these values, and you W 0 comma 2 value is 2 at this stage. Then we will compute C of 0 comma 2. So we take minimum of 0 less than K less than equal to 2. So C of 0 comma 1 minus 1 plus C of 1 comma 2. Then C of 0 comma 2 minus 1 plus C of 2 comma 2. So here what happens is we have I and J as 0 and 2, but K value we have 1 and 2. We have two different K values. So among them what we have is we get minimum of 0 plus 7, comma 7 plus 8. So obviously minimum of these two is 0 plus 7, which is 7, and this 0 plus 7 we got it for K1 when K values was 1, and its cost is 19. So we fill up 0 comma 2 for cost as 19, and for K1 we got this minimum value, so root 0 comma of 0 comma 2, 0 comma 2 will be 1. So whichever K value gives us the minimum, that is going to be the root. In the same way, when I becomes 1, J will be I plus 2, so J will be 3. So we have 1 less than K less than equal to 3. So we get K value as 2 comma 3. With that, we fill up the cell 1 comma 3, because I is 1, J is 3. So we fill up this cell for W, C and R. So here when we calculate W, we have the W1 comma 3, we got 9. So we are filling this cell with 9. And then we have C. Now here we have we substituted the equation, the values. We have 0 plus 3 comma 7 plus 0. Obviously 3 is minimum, and we have plus W value, which is 9. We get the result as 12. So 1 comma 3 for cost will be 12. So we have filled up this cell. Then which value gave us 12? Which K value? K is 2 comma 3. So this first part is for 2 and the second part is for 3. So K value 2 gave us the minimum cost. So R of 1 comma 3, we will fill it as 2. That is, A of 2 will be the root node between K2 and K3. That is, if we select two nodes, if and int, if is going to be the root node of this tree. Then we continue with the third set, taking I value as 2, J will be 4. So K value will lie between 3 and 4. So K will be 3 and 4. So we compute this, fill up the same cells, and what we have is we have 0 plus 3 as well as 3 plus 0. So here you can consider, even K3 is giving us minimum value, even K4 is giving us minimum value. So we can consider anyone, but what happens is, actually when when it's an algorithm and when you try to solve it, obviously we are going to take the minimum, the first value, whatever we get as the minimum value. So here we pick up 3. So K is 3, both are giving, so but we are picking 3 as Kth value. So we have 2 comma 4 as 3. So this way we have taken two nodes. So J minus I is 2, such that we fill up the upper diagonal of this, all the 3 matrices. Now next stage, we take 3 nodes at a time. So J minus I will be 3. So J will be I plus 3, and starting from I equal to 0, we have 0 less than K less than equal to 3. So now K is going to have 3 values, 1, 2 and 3. So we will be at this stage. So we will be taking 3 nodes now. Do, which is 1, if, which is 2, and int, which is 3. And we will be finding the cost as well as which cost gives us the root of that tree with 3 nodes, do, if, and int. So same way we have performed. Now here if you see 0 plus 12, 8 plus 3. 8 plus 3 is 11. 19 plus 0. So 8 plus 3 is minimum. So who is giving minimum value? Which k? It is k2. K2 gave us the minimum value. So root will be 2. So we will fill up 0, comma 3 of r as 2. In the same way, when I becomes 1, j becomes 4. And we have k value from I less than k less than equal to 4, which is 2, 3, and 4, excluding 1, because k is 1 less than k. It's not less than equal to. So starting from 2, 3, 4, we compute the W weight, we compute cost, we also compute R. And even here, if you just substitute these values, we get 2 as the k the value, which gives us the minimum cost. So we fill up the cost as well as we fill up 1, comma 4 as 2. Then finally, we consider all 4 nodes to fill up this set 0, comma 4. I, comma j will be 4 now because we are considering all 4. So j will be equal to I plus 4. And now starting from 0, I0 less than k less than equal to 4. We will have k values as 1, 2, 3, and 4. That is all 4 A1, A2, A3, A4 elements are considered. And we have to find which one will give us the which one is going to give us, which k value is going to give us the minimum cost. Now we substitute in the equation, and here we can find that k with value 2 is giving us the the cost value as the least one. So cost is 32, and kth value 2 we have, which gave us the minimum cost, is filled in the root of 0, comma 4. So this way we use I minus j as 0, fill up the diagonal elements, then j minus I as 1, let us consider only one node, fill up the upper diagonal, then the same way continue with j minus I is 2, j minus I is 3, j minus I is 4. If we have n number of nodes, we will continue this till j minus I equal to n. So this way we compute. Now the topmost corner, that is the top right corner cell, is giving us the minimum cost of the binary search tree. And this is going to be the optimal cost. The cost is, we don't not bothered about W, we are bothered about cost. Cost is 32. And the root is 2. That is the upper top right cell 0, comma 4, which is 2. So element if becomes the root node, and that tree is going to have the optimal cost. It will be optimal binary search tree with cost as 32. Now let us look at how to construct this tree. Here we have stored the root values at each stage, considering no nodes in the tree. So root is 0. Then we considered one node at a time in the tree, and we computed who's going to be the root. So obviously when it is one node at a time, first node is going to be root, second node is going to be root when it is selected. So only one node at a time is selected. So we have 1, 2, 3, 4 values. Then we considered tree with 2 nodes at a time. So we got this value, this diagram. Now we will try to look at the R table, and from this matrix or R table we will construct the tree. Now this cell of R of 0 comma 4 is going to give us the root. It is 2. So which element is 2? A2, which is if. So here on the right side we will write 2 number node, and then later we can create that tree. So we have 2 as the root. Then who is going to be its right child? Now what we do is we consider who's going to be the right child and who's going to be the left child. So we will consider the row here. Now we will look at where does the value 2 change. So here if you see we have 0 comma 4 0 comma 4 as 2, 0 comma 3 as 2, 0 comma 2 as 1. Now here the value is changing. Now this change is still where? This change is still 0 comma 1. 0 comma 1. So the left child from 2, we are considering the row. So what we get is from 2 the change is 1. So the left node will be 1. The left node will be 1. Then what about the right child? The column will give us the right child. So from 2, the second, if you look at the column, is going to give us the right nodes. So what we have for 2? Now 2 changed to 3. So when 2 changed to 3, right child of 2 will be 3. Right child of 2 will be 3. And then, so we right now have 2 with 1 as the left child and 2 with 3 as the right child. Now which node is left? Node 4 is left. Now do we have node 4, the value 4 in this row? No, we don't have it. Do we have it in this row? Yes, we have it. Where do we have it? After 3. So when we have it in this column, that means that it's going to be the right child. Right child of whom? Right child of 3, because after 3 the value got changed. So right child of 3. So here we have node 4 as the right child of 3. Now these t values is going to, t of 0 comma 4 is nothing but the cell. T of 2 comma 4 is the cell which gave us 3. T of 3 comma 4 is the node 4. Now what about the other t's? This one, 1. It's 0 comma 1. Now what about the other tree values? All others gives us the external nodes for unsuccessful search. So here you can find t of 0 comma 0 is 0. So obviously it's going to be the right, the left external node. 1 comma 1 is 0. So it's going to be the right external node of 1. So if you consider this part, this section, you have 1, 0 is the left node, 0 is the right node. So we got this tree, subtree. Then if you go further, move further, 3 is there. 3, 2 comma 2 for 3 is 0. That gives us the external node for 3, left child, for unsuccessful search. For 4, look at this part. We have 0 this side, which is 3 comma 3. We have 0, this should be 0 this side, which is t of 4 comma 4. So this way we can find, using this root node, root table, we can find, or we can construct the actual tree, which is going to be the optimal binary search tree. Now replacing these values of 2, 1, 3 and all these numerical values with A1, A2, A3, all these indices with A1, A2, A3, we get this as the tree with F as the root node, do as its left child, int as if it's a right child, and while as int int as if's right child, and while as int's right child, and its cost is going to be 32. So this is how optimal binary search tree is computed. Now, this is a very hectic problem, or so far, whatever problems we have seen, we never had these many calculations. And this one is the most complex part, but just remember the equations and follow, substitute the values of I and j, and then try to construct the W matrix and the cost matrix as well as the root matrix, and from there we can figure it out which tree is going to have, or what is the tree and what is its minimum cost. So this is how optimal binary search tree is done. Now, usually in exams, you are not will be given such a big equation to compute, or these tables to compute. But optimal binary search tree is one of the important topics, and definitely you will be some type of theoretical questions can be asked, but usually they have not, is not going to ask such a big computation to be done in exam. So, but remember that this is how it is done, and if it is the question asked, you have to definitely state these three equations, and then you have to just summarily explain theoretically how these equations will lead you, or give, that is the table that is constructed, and how this is going to lead you to an optimal binary search solution. So this is all about the optimal binary search trees. Now your textbook has constructed this, the textbook which is prescribed in the syllabus has taken a different approach of computing the values, the table. Now, for sake of simplicity, I have taken three different tables for W, C, and R. But the textbook which is prescribed has computed all these values in one matrix. Sorry, in one matrix, and each cell contains its C, its W, its R value. So it's same as what we have seen here. The other difference is that we are constructing the triangle. If you see the diagonal triangle here of the matrix, starting from the diagonal going to the top right corner. The textbook has done it the other way. It's coming from, it's what you call mirror image. So that way it doesn't matter, but the value is going to be same. It doesn't matter how you compute, how you create table. The only thing is you have to apply this equation and try to calculate the cost and construct the tree. So this is all about the optimal binary search tree. It's the algorithm is given in the textbook, and it's not, algorithm is much easier than the way or complex way we are computing. The algorithm has all an array, the matrix for W, matrix for R, matrix for C, and it's all going to have for loops, and we is going to use a condition to find which k is minimum, and then fill up all the values. So this way we will be computing, or we have the algorithm for optimal binary search tree. So when the question asks, theoretically, you also have to write the algorithm. Algorithm just contains for loops with the matrices. So it's very easy to remember. If you remember the equations, writing the algorithm will also be much easier. So this was the most complex actually topic about most complex topic of dynamic programming, that is optimal binary search tree.